Welcome to my YouTube channel. Today I want to quickly talk about the polarity and the polarity of the molecules. So for the polarity of the molecules, one essential thing is to know electronegativity. You would be provided with the table of the electronegativity. There's only one thing I want to know about electronegativity. In the periodic table, fluorine with the symbol F is the most electronegative element, and oxygen with the symbol O is the second most electronegative elements. And you should know this, that is the only thing. Also, when you move in the periodic table from the, let me just grab my periodic table now here, if I could do it fast enough, there you go. So when you move from the right to the left, you could see that there is actually metals which are least electronegative, and electronegativity actually increases as you go to this part. Also, when you move from the bottom to the top, the electronegativity increases, and that's why fluorine is, by the way, noble gases are exceptions. They don't have electronegativity, they are reluctant to react, they don't have electron affinity. That's why fluorine is the most electronegative and why oxygen is second most electronegative. The trend is more harsh here than from bottom to the top, although there is a trend that from bottom to the top also the electronegativity slightly increases. So that is good enough for you. Also, it would be, if it's a hard judgment, you would be provided with a table to judge. Let's go to molecules, and for electronegativity I would suggest that you go back and review the Lewis structures, because that's the basic thing here. Let's talk about a molecule like CO2. This molecule that I have a model of here. Okay, electronegativity of oxygen should certainly be bigger. We do show the electronegativity with a kind of arrow that points up to the more electronegative atom, and we just do this at the tail to show that it's a positive or less electronegative atom. So that's how we do that. We also have another electronegativity vector. This we call polarity or electronegativity vectors. And then once we draw all of those electronegativity vectors or polarity vectors for all the bonds, we could certainly judge and see what happens. Two of those vectors are pulling and in opposite direction. It's just like they're canceling out one another, and the molecule totally becomes non-polar. So this is non-polar. What about Ch4? Well, about Ch4 there's much to talk, but what I want to show you is two judgments on tetrahedral structures, okay, or structures that is coming from tetrahedral framework. You could judge two of these bonds together and sum up the vector, or you could judge three of these bonds together and sum up based on your molecule and your shape of your molecule. Let me just grab this and talk about the Ch4 molecule. Okay, so we could say that the two over here are pulling in this direction. It's as if it's one hydrogen pulling in the direction that is right in between. Okay, and also we could also see that for the other two, when I put this in the center, and I could ignore actually this one, the other two also that are pulling right up would actually put my other hydrogen in between, and you could see that the two hydrogens that I'm holding with my hand are pulling in opposite directions, so they're just canceling up. I could also show this in a figure. With this demonstration it would be easier for you to understand. I do the molecule, the methane, in black, and I do the overall thing in red, so that you could see how the two would cancel out. Let's take these two for example. They pull with the charge of one hydrogen, with the power of one hydrogen, and also these, And actually the electronegativity for hydrogens are less than carbon, so they're pushing in this direction with the force of one hydrogen, and also pushing in this direction with the force of one hydrogen. So you could see the two opposing forces would actually cancel out. So that's why how to say, a methane molecule is sort of nonpolar as well. There's also one other judgment we could do for the same exact molecule, methane, and that is to see what now if I take these three together and assume what happens. The overall vector would be just one pulling down with at the very base, like this place, pushing right down. Okay, so it's as if just one hydrogen is attached here, this one pushes in and this one pushes back. So you could see that these are exactly the opposite forces, and it would also cancel out. So I could say that this three, this one, and this one, they push up together. Also this one pushes down and they cancel out. So it's still nonpolar. So there are these two sort of judgments that is important when you do talk about tetrahedral geometry. Okay, also let's do talk about BH3. For the BH3, that's the trigonal planar geometry. The same exact story holds. You could take this one. Now for BH, H is, I believe, a little bit more electronegative, so it's pulling this time, and these two are pulling with the exact same force right in between the two. And if I have a very good trigonal planar framework, it would be one that is right in between. The two would cancel out, so the molecule would still be nonpolar. Okay, that's this. Let's move on to more examples. I want to talk about the polarity of, let's see, I have a lot of molecules to talk about polarity. Okay, let's go to CHCl3, and I have a model of that to make it easier. And with that you could see that now I have to take the three chlorines as if one chlorine is pushing down. So it's like telling me that with CHCl3 I have a CH, and my three chlorines, the three chlorines are more electronegative than carbon because they're group 7, so they're pulling down all of the three, and the hydrogen is also pushing. So there's a net polarity vector moving the molecule down, so this molecule is polar. Let's also do CH2Cl2. For this molecule, the CH2Cl2, we could use the rule of 2 of those bonds to actually do that. Let's use green for the framework. Okay, now we could say that the chlorines are pushing. The overall effect would be one polarity vector with the same force of one chlorine pulling in this direction, and the two hydrogens pushing, because hydrogens are less electronegative, is the force of one hydrogen pushing down. So it's a net polarity vector in this direction, and the molecule is also polar. Okay, so that's this. I wanted to also talk about other molecules. Let's see, we have the NH3 molecule that I wanted to talk about, and that's also a good example of how we talk about the NH3. It's a pyramidal based on a tetrahedral framework. Okay, a tetrahedral framework with just one lone pair would give the result of NH3, so that's the NH3, and you could assume that the three of these hydrogens would mean that you have one hydrogen that is right from beneath attached to this. That would be the overall effect, and it's pushing towards nitrogen because nitrogen is more electronegative. So right from below with the force of one nitrogen and its electronegative net polarity vector, so the molecule is still polar in this example, NH3. Let's also do yet another structure, the structure of H2o. Water molecule is also interesting. This is like this, and you could see that the result would be oxygen is more electronegative. The result would be this. So you have a polarity vector pushing upward, another polarity vector. The result of two would be just one polarity vector with the force of one hydrogen pushing up. Okay, so there's a net polarity vector and the molecule is polar. That's why water is such a beautiful, strong solvent. Let's talk about the Sf4 structure. Sf4 has a kind of structure that is seesaw, and that's with sulfur in the middle, 1 fullerene, 2 fullerene, 3 fullerene, and 4 fullerene, and 1 lone pair. So it's a trigonal bipyramidal framework and makes a seesaw with 1 lone pair. You could say that these 2 fullerenes that are pulling in this direction will give you one that actually is in this direction, and the one that pulls up cancel the one that actually pulls down. So although these two are cancelled out, but you would still have one polarity vector, one net polarity movement in this direction, and the molecule would still be polar. Let's talk about IF3. IF3 is also one of those molecules that is trigonal bipyramidal in nature. So that's I in the center, and you've got 2 lone pairs and 3 fullerenes. Okay, that's IF3. So if you look, the 2 iodines on top and bottom cancel out, but there is a polarity vector that can't be cancelled, so the molecule still remains polar. Let's talk about PF5. PF5 is another example where you have a full trigonal bipyramidal framework. So that's the structure for it. PF5, 3 fullerenes in plane position, 1 fullerene in the top, 1 fullerene in the bottom. Here in this example, when you look, there's 1 fullerene that pulls in the upward and 1 that pulls downward. They cancel out. 1 fullerene that pulls in this direction, and the overall effect of these two is right in between, so 1 pulling in this direction. So here, opposing to the previous example of IF3, this one is now canceling out. Okay, so the molecule remains non-polar. Okay, that's about PF5. Let's see if I don't have any other example. I should as well wrap this video up with let's do 2 more examples. Let's see how much time I do have. We have still plenty of time, so I could do 2 more examples. Let's do XeF4, which is sort of XE, a lone pair on the top, a lone pair in the bottom, and then 4 fullerenes. And then you could see that these 2 fullerenes that are pulling in this direction would pull, the overall effect would pull out right in between. For these 2, it's also the same exact story, and the 2 would cancel out, so the molecule is non-polar. Also, let's talk about the case where we have SF6, that is also an octahedral framework, and just like the symmetrical case of PF5, where we saw the cancellation of the polarity vectors, here as well you could see that the 2 fullerenes that will pulls up and down would cancel out, And just like we see for the previous example, the two fullerenes on this left side, you could also take these two on the back and front. It's not easy to show that on this two-dimensional representation. It's easier to take these two. So one that goes in between them, the polarity vector, the overall effect of that polarity vectors, also the overall effect of these two fullerenes is another right in between that would cancel out, and then this would also be non-polar. Before I wrap up, I want to also mention one tricky case of O3. Let's say O3 is this. So you could say, okay, oxygen and oxygen, there's no electronegativity difference. Oxygen has an electronegativity of 3.5, and you can't say there's a polarity vector because there's no, there's no polar electronegativity difference. So even though the bonds are non-polar, you could still look at the central atom to judge if there is a slight polarity for O3 molecule. And if you look, that's a trigonal planar framework where you have a lone pair in one end of it. A lone pair is more, electron rich than the bonds themselves. Electrons on the bonds are shared electrons, whereas this lone pair is lonely. So you could say it's slightly pulling the molecule towards that part, or better, it would actually have a slight polarity towards there, because these are shared electrons, so they don't have tendency to pull, but the lone pair are pure source of electrons, so they could pull up. So if the molecule is, even the bonds, if the same elements apply, if even the bonds are going to be non-polar, the molecule could still be polar if it's not symmetric. Okay, so things like this one, O3, or NH3, if you have a molecule that has this structure and all the same atoms, it would still, because of the asymmetry of that lone pair on the top, it would still be non-polar. Okay, so this is also, my bad, polar. It's slightly polar because even though the bonds are non-polar, the molecule is slightly polar because of that lone pair. I want to wrap it up here for this video on polarity vectors, and I hope if you go back, review the Lewis structure or the videos on Lewis structure, you could have a good comment on the polarity of any molecule that we are interested to know about their polarity. Okay, let's wrap it up for now.